Good afternoon, class. We are looking at practice test number 2, module 2, chapters 3 and 4. Chapter 3, polynomial and rational functions. Chapter 4, exponential and logarithmic functions. And here's chapter 3, polynomial and rational functions. The price demand function of a company that manufactures bats, a large tank or top, is given by P of x equals minus 5x plus 6,000. Find the revenue function. Revenue function, by definition, is the product of the price and the number of units sold times x. So minus 5x squared plus 600x. The company's fixed monthly cost is $1,563, and each unit costs 10 bucks. Write the cost function C of x, where x represents the number of packets of bats. So C of x in essence is mx plus b, 10 times x for each one, and a fixed cost of 1563. So C of x is 10x plus 1563. Find the profit function. By definition, capital P, the profit function, is revenue minus cost. So basically, subtract the cost function from the revenue function. So we are going to distribute the negative side we combine like terms. We get minus 5x squared plus 590x minus 1563. How many bats must be produced and sold in order to maximize profit? Notice the function is a quadratic function with the leading coefficient to be negative. A is negative 5. That means it's a parabola that opens down. That means the graph looks like that. So the maximum occurs at its vertex, x equals minus b over 2a. So A is negative 5, B is 590, C is negative 1,563. So minus 590 divided by 2 minus 5. This is negative 10, and we end up with 59. What is the maximum profit? So basically plug in. Remember, we want in essence the y coordinate of the vertex. So plug into the profit function and use a calculator, evaluate it, and you get $15,842. That's the maximum profit. What price must the company charge in order to maximize profit? Here's the price function. And plug in x equals 59. Minus 5 times 59 is negative 295 and 600, $305. That's what we should charge. The polynomial of degree 3, P of x, has a root of multiplicity 1 at x equals minus 6, and a root of multiplicity 2 at x equals 4. P of x passes through the pair 2, 8. Find the formula for it in factored form. Well, x equals minus 6. That means there's a factor of x plus 6. X equals 4. That means there's a factor of x minus 4. This has multiplicity 1. You're fine with that. This has multiplicity 2. That means x minus 4 squared. What is the leading coefficient? We don't know. We call it a. So a times x plus 6 times x minus 4 multiplicity 2. You use this pair, replace the x with 2, the y or p of x with 8. So if you plug in 2, you get a times 2 plus 6, 2 minus 4 squared. So this is 8. Negative 2 squared. 8 cancels out the 8. This is positive 4. 4a is 1, a is 1/4. Replace the a. P of x becomes 1/4 x plus 6 times x minus 4 quantity squared. And again, they want it in factored format. Otherwise, you can raise this to the power of 2, multiply by this, and 1/4. Divide using synthetic division, express the answer as f of x equals, as f of x over d of x equals q of x plus r of x over d of x. So to do the synthetic division, we have to make sure both pieces are in descending order. They are. And so we just write the coefficients 3, minus 2, 1, minus 4. And if there is any term missing, you have to have a 0 as a placeholder. Division by x plus 1, that means you need a negative 1. So you drop the first one just the way it appears. Then you multiply by this number. You get minus 3 and minus 2. They add up to minus 5. Again, you multiply by negative 1. You get positive 5 and 1 is 6. Multiply by negative 1. They add up to negative 10. And you are going to write this accordingly. The degree here is 3. The degree here is 1. And you divide the resulting quotient has to start with the degree 2, 3 minus 1. 3x squared minus 5x plus 6 plus negative 10 over x plus 1. So this ratio can be represented in this format. Consider the function f of x equals 2x cubed minus 8x squared plus 5x plus 3. List all the possible rational zeros of f. What is rational zero theorem? According to that, factors of a sub 0 over factors of a sub n. F of x starts with a sub n x to the power of n, and it ends with a sub 0. So factors of the constant, 3, over the factors of the leading coefficient a sub n, which is 2 here. Factors of 3 are plus minus 1, plus minus 3. Factors of 2, plus minus 1, plus minus 2. So if you divide by plus minus 1, you get the numerator. If you divide by plus minus 2, you get plus minus 1/2, plus minus 3/2. And those are possible rational zeros. Now, find the rational zeros. You have to check, meaning we go with the factor theorem, we plug in negative 1/2, positive 1/2, negative 1, positive 1, so on and so forth. And you can go with the easy numbers first. Don't do the fractions, plus minus 1, plus minus 3. So it does take a little bit of a time. But what happens when you plug in 3? You get 2 times 3 cubed. It's 54. 3 squared is 9. Minus 72. Plus 15 and plus 3. They end up with 0. So that means 3 is a 0. That means the function has a factor of x minus 3. To find the remaining zeros of f, we divide this by x minus 3. And to do that, we can go with the synthetic division. 2, negative 8, 5, 3, and inside is 3. And remember, has to be in descending order. It is. Nothing has to be missing. If anything is missing, you use a 0 placeholder. So you drop the 2. You multiply by 3. And you add these 2. You get negative 2. Again, you multiply by 3. And you add these 2. You multiply by 3 again. And you add this to 0 because the degree was 3 here and degree 1. This one has degree to 2x squared minus 2x minus 1. Because this is a quadratic equation, we can use factoring, or if it's not doable, the quadratic formula. So we're going to use quadratic formula on that because it can't be factored. And we call ax squared plus bx plus c equal to 0. X is minus b plus 1 is a squared of b squared minus 4 is equal to a. In this case, a is 2, b is negative 2, c is negative 1. We plug in. So we get minus negative 2, which is 2, plus minus the square of negative 2 squared, which is 4, plus 8, and that becomes 12. In other words, this is 4 plus 8. Now, 12 is 4 times 3. So we get 2 plus minus 4 comes out as 2 square root of 3 divided by 2. It is very important to know you can't drop these 2, but you have to factor the 2 from the numerator. When you do that, you get 2 times 1 plus minus the square root of 3 over 2. You drop them, and those are the answers. Factor f using the zeros of f of x. So we write it in this fashion. We had the first number 3, so it's x minus 3. 1 minus square root of 3, so x minus that. 1 plus square root of 3, x minus that. And that's the factored format. Consider the function f of x equals x to the power of 4 plus 2x cubed plus 22x squared plus 50x minus 75. And we want to find f of 1. That means plug it. So this is 1, this is 2, this is 22, this is 50. So this is 1, 2, 22, 50. Add up to 75. Minus 75, now it's 0. F of negative 3, I'll leave it for you to evaluate it. That ends up being 0 as well. Now, if we were to use rational zeros, would be factors of the constant negative 75 over the factors of 1. 1, just the factors are plus minus 1. So basically the factors of negative 75, plus minus 1, plus minus 3, plus minus 5, plus minus 15, 25, 75. Those are the possible rational zeros. And 2 of them happen to work out, in this case 1 and 0, and there may be more, but as long as you have 2 of them, remember this is degree 4, so if you have 2 of them, you can multiply. This means x is, you can divide by x minus 1. This means you can divide by x plus 3. So if you divide by those, the product of those two, you get a quadratic function. You can figure out the next. As far as finding it if you were on your own. However, you can use technology, perhaps second calculator 0, or try these numbers one by one. And we already have 2 of those working. If 5i is a 0 of a function, find the remaining zeros of f. There's one more 0, and this is using conjugate 0 theorem. If p of x is a polynomial with real coefficients, and if r is a plus bi is a 0 of p of x, then the conjugate r bar a minus bi is also a 0 of r of p of x. Therefore, 5i is a 0, so is minus 5i. So f of x in a factored format would be x minus 1 times x plus 3 times x minus 5i times x plus 5i. And these two, if you want to combine them, recall a minus bi times a plus bi. I showed you that it becomes a squared plus b squared. So this would be x squared plus 5 squared, which is 25. Find the domain of the following function. Express your answer in an interval notation. Well, any rational function, for that matter, any fractional format, you set the denominator equal to 0, you exclude it. Factoring is easy. You want 2 numbers. The product is -8. The sum is -2. So x plus 2x minus 4. So x is there -2 or +4. So what is the domain? All real numbers except these 2. We have to exclude them. How do we exclude them? Minus infinity, comma -2, parentheses union -2, 4, union 4 to infinity, parentheses, means exclude the endpoints. Use the remainder theorem to evaluate this f of x at x equals 2. Simply put, plug in, everybody. That's all it means. Plug in. So replace the x with 2. This is 16, so 6 times that, minus 8, 15 times 4, minus 15 times 4, this is 4. 6 times 16, 96, minus 8, minus 60, plus 4, minus 7, and they add up to 25. Show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. Find the remaining factors. Use the factors to determine the zeros of the polynomial. There are 2 ways to do that. We can divide this by x plus 2 using synthetic or long division. Or we can go with the factor theorem, simply evaluate f of -2, because when you divide by x plus 2, you have to evaluate f of -2 and observe. So plug in -2. -2 cubed minus 6 times -2 squared minus -2 plus 30. Minus 8. So let's put minus 8 up here. This is 4. 24 plus 2 plus 30. As you can see, they add up to 0. And we showed that this is a fact. If you want to go with the synthetic division, you put these numbers 1, -6, minus 1, and 30, and then x plus 2, you put a -40, and you do the rest. You know, drop the 1, then you multiply by -2. Same thing here, same thing here, and this proves that. Okay, now so you're dividing this by this. This has degree 3, this has degree 1, so this must have degree 3 minus 1, so 1x squared, or simply x squared, minus 8x plus 15. So this is the product of x plus 2 and x squared minus 8x plus 15. This can be easily factored because you want two numbers, the product is 15, the sum is minus 8. We get x plus 2, this is x minus 3, x minus 5. So what are the zeros? Well, we already know one of them is minus 2. This is 3, this is 5. By the factor theorem, the zeros of the functions are minus 2, 3, and 5. Given the function f of x equals x plus 4 over 2x squared plus 11x plus 12, find the domain of f in interval notation. We are interested in finding in graphing, so we're going to go over the details. And so to do so, we start with the domain, and even to do so, any fractional format, any rational function. The first question is, can I simplify it? And you try to factor it, and 2 is a prime number, so you have x and 2x. And 12 is the product of 1 and 2, 2 and 6, 3 and 4. It ends up working with 4 and 3. Notice this is 8x, this is 3x, they add up to the middle term. And so x plus 4 cancel out, but it doesn't change the fact that x can't be negative 4. The function reduces to 1 over 2x plus 3, but it doesn't change the fact that x can't be negative 4. And of course here, x can't be negative 3/2. So there are two numbers, so x can't be negative 4. X can't be negative 3/2 either. So we write the domain is from negative infinity to negative 4, union negative 4 to negative 3/2, union negative 3/2 to infinity, and they all take parentheses because the endpoints are not included, everybody. So that's the domain. Find the asymptotes of f of x as well as any holes. First, I want to discuss the holes in a rational function. In the case of a rational function, there is a hole if you can find a common factor from the top and the bottom, because you can drop the common factor, but you cannot drop the fact that x can't be the other one that becomes 0. So x can't be negative 4. So at x equals minus 4, for this function creates a hole for this function. So if we plug in negative 4 here, we get 2 times negative 4, negative 8, and 3 is negative 5, 1 over negative 5. So negative 4 and negative 1/5. That would be the location of the hole. One, two, three, 4 on the left, so 4, negative 4, and this is 1. So roughly here. So that's how you get the hole. Vertical asymptote. So x equals negative 4 is not a vertical asymptote. It's a location of a hole. So 2x plus 3 equal to 0. X equals minus 3/2. That's your vertical asymptote. And you graph that. This is negative 1. This is negative 2. So in between, x equals negative 3/2. Now, as far as horizontal asymptote is concerned, I want to remind you, if you have f of x equals n of x over d of x, where the numerator is a sub n x to the power of n all the way to a sub 0, and the denominator is b sub m x to the power of m all the way to b sub 0. When n is less than m, horizontal asymptote becomes y equal to 0, which is the case here because the numerator has a degree 1, degree 0, and the denominator has a degree 1. So y equals 0 or the x-axis. However, if n is equal to m, the leading coefficients take over. Y equals a sub n over b sub n. And if n is precisely n plus 1, you do division. This becomes a linear function giving rise to y equals mx plus b as a oblique asymptote. You either have horizontal or oblique asymptote and not both. Find the intercepts. Well, we are going to find the x-intercepts and the y-intercepts. In order to find the x-intercept, you set y or f of x equal to 0. A fraction is 0 when the top is 0, and there is no x-intercept. The y-intercept, if you set x equal to 0, you get 1/3. So there is no x-intercept. And the y-intercept, you set x equal to 0, you get 1/3. Again, a fraction class, any fraction is 0 if the numerator is 0. In this case, the numerator is a number. It doesn't matter, large, small, negative, positive, makes no difference. So that's 0, 1/3 roughly. Locate at least 1 point on each side near the vertical asymptote. In order to graph a rational function, as long as you have a point or two on each side of a vertical asymptote, this has only one vertical asymptote, which gives you two sub-intervals, to the left and to the right of it. To the right of it, you do have a point. Remember, this is your horizontal asymptote, this is your vertical asymptote. The graph will not cross the horizontal asymptote because horizontal asymptote, that means x-intercept, and we showed that there is no x-intercept. So it never crosses it. So this means it either goes like that or like this. So one point we have, it goes like that. Same thing here. You don't have an x-intercept, it doesn't cross it. So either goes like that or like that because of the hole has to go like that. But in any event, you can pick a pair, for example, easy number. If x is -2, we get the -4 and 3, -1, 1 over that is -1. If we pick -1, we get -2 and 3, +1, so the answer is 1. So we can pick those two pairs, and now we can sketch the graph. And we're done. Given the function, find the domain of f in interval notation. Well, remember, set the denominator equal to 0, x becomes 3, and exclude that. So x can be any number except 3. Minus infinity to 3, union 3 to infinity. It's very straightforward. Find the asymptotes. Vertical asymptote, x minus 3 equal to 0, x becomes 3. So x minus 3 is 0, x equals 3. We don't have a horizontal asymptote. The reason we don't, because the degree of the numerator, and by the way, that would be this line. The degree of the numerator is larger, and if we multiply this, we get x squared. This is x minus 5x, they add up to minus 4x, and then minus 5. Now you are going to divide, because the degree difference is 1, you are going to divide using any method you want. You end up with x minus 1 minus 8 over x minus 3. I'm assuming everybody has an easy time with the division by now, either synthetic or long division. This is the first degree, so y equals x minus 1 becomes the oblique asymptote, and there is no hole. Why is this oblique asymptote? By definition of oblique asymptote I went over. Why there is no hole? Because there is no common factor between the top and the bottom. So you can pick a couple of pairs, for example, 0, -1, 1, 0, to graph this line. So 0, -1 here, 1, 0 here. So it becomes that. Intercepts. X is 0, find y, y is 0, find x. And it's very easy to see how we find them. To find the x-intercept, set f of x equal to 0, which means set the numerator equal to 0, which means x is -1, x is +5, and therefore -1, 0, 5, 0. One more time. How do you find x-intercepts? Set y equal to 0. X-intercepts y or f of x. When f of x is in the form of a fraction n over d when n is 0. So set this one equal to 0. X is -1, x is 5. Those are the answers. So you can plot those pairs, -1, 0, 5, 0. So we have those two pairs. Y-intercept, everybody, when x is 0, and it's probably easier to go with this one. When x is 0, this goes to 0, -5 over -3, or 5/3. 0 and 5/3. 5/3 is 1 and 2/3, so it's between 1 and 2. So somewhere there. And now, locate at least one point on each side near the vertical asymptote, sketch the graph. Well, we already have one point here. So this is really the graph. And we have a couple of points on this side, so that's the graph. You don't need to locate any more. And if you pick any other point to the right or left, gives you somewhere in these two regions. And that would be the graph. Let f of x be x over x minus 2. Sketch a graph of f using technology to determine whether f is a one-to-one function. So you graph it pretty fast. It is a one-to-one function because it passes HLT, horizontal line test. If it's one-to-one, find its inverse, F inverse. Well, we're going to call f of x y just to make life easy. To find the inverse, interchange x and y. This becomes x, this becomes y, this becomes y. Now you have to solve for y. So you cross product here, you get x times y minus 2x equals 1 times y over y. You move things around. And you do the factoring. You divide by x minus 1 and you call it f inverse. So we have the function, we have its inverse. And we can graph this using technology again. And what I want you to notice is VAs versus HAs, vertical asymptotes and horizontal asymptotes. So you have the vertical asymptote here, horizontal asymptote here. And by the way, it's very easy to see that x equals 2 is the vertical asymptote here, and y equals 1 is the horizontal asymptote. So now it has the vertical asymptote x equals 1, horizontal asymptote y equals 2. Domain of f, going back to the original function, x minus 2 equal to 0, x equals 2, exclude that. So from negative infinity to 2, union to infinity. We want the rest of them, and start with the bottom one. The domain of f and range of f inverse are the same. Put it here. That means for f, x, this is the situation with x. X can't be 2. This is the situation with y. Y can't be 2 for f inverse. Domain of f inverse, x can't be 1. So negative infinity to 1, union 1 to infinity, the same as range of f, negative infinity to 1, union 1 to infinity. Solve the following inequality, graph the solution set, and write the solution set in interval notation. And to do so, we are going to use there are two ways you can graph this. The portion above the x-axis is the answer because you want positive, including the x-intercepts. However, a fast and easy way, we go with the sign graph. We are going to factor the numerator. Set each one equal to 0. So this gives you, if you set the top equal to 0, that gives you x equals negative 3 and 6. If you set the denominator equal to 0, gives you minus 2. You put them on a number line from smallest to largest. And if you call this f of x, so x and f of x go, x, this is the number line goes from negative to positive infinity. These three numbers, okay, in order, negative 3, negative 2, 6, at negative 3 is 0. At 6 is 0, at negative 2, because it belongs to the denominator, is UD, undefined. Then you use TPs, test points. Negative 4 here, negative 2.5 here, 0 here, 7 here. Now, here's what I want you to see. When you look at this one in factored form, this has exponent 1, exponent 1, exponent 1, or better yet, odd exponents. If it's even, then both sides have the same sign. If it's odd, they alternate. And if you plug in 0, and it's easier to go with this one, negative 18 over 2 makes it negative here, and the rest of them alternate. If you have doubts, plug in the test points, negative 4, and you put it into factored form. As an example, here's negative, 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 and negative times negative over negative is negative. That's how you find them. Now, what's the answer? Going back here, we want greater than or equal to 0. That means positive, positive. So this means from negative 3 to negative 2, union 6 to infinity. Now, negative 3 belongs to the numerator. So because we have the equality, it's included. But negative 2 is not included because it's undefined. 6 belongs to the numerator and it's included. And on a number line, anywhere from negative 3 to negative 2, this is a solid point, this is not. And over here, anywhere from 6 to infinity. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x equals a sub n x to the power of n all the way to a sub 0. it will look like y equals a sub n x to the power of n. This is known as the n behavior of a function. So if the degree is, we're talking about this, if the degree is even and the leading coefficient a sub n is positive, it looks like y equals x, meaning x goes to negative infinity or x goes to positive infinity. In both cases, f of x go to positive infinity. We are talking about the first and second quadrant as the n behavior. If a sub n is negative, then it's just like a parabola that opens down. Whether x goes to negative or positive infinity, in both cases, f of x goes to negative infinity. If the degree is odd and the leading coefficient is positive, looks like x cubed. If it's negative, looks like minus x cubed. In the case of x cubed, the first and the third quadrant, meaning x goes to negative infinity, so does y or f of x. X goes to positive, f of x goes to positive infinity. In this case, x goes to negative infinity, y goes to positive infinity, x goes to positive infinity, y goes to negative. Theorem, behavior near zero. Multiplicity. X minus c has the multiplicity m when it's being raised to the power of m. If m is odd, f crosses the x-axis at c0. If it's even, it doesn't. So for example, here or here, it crosses 0 with multiplicity of odd, 3 in this case, and this is 2. The higher the multiplicity, the flatter the curve is at the 0. The sum of the multiplicities is the degree of the polynomial function. Graph the following polynomial using the n behavior and behavior near x-intercept. First, let's put this in factored format to find the intercept. Makes life easier. So put these two together. X squared times x minus 5. Put these two together. Minus x minus 5. So x minus 5 is in common times x squared minus 1. And as you know, x squared minus 1 is x plus 1, x minus 1. So this is completely factored out. So we have 3 x-intercepts, 5, 0, negative 1, 0, positive 1, 0, and all of them have a multiplicity 1. So those are the 3 pairs. Y-intercept, it's easier to go to the original one. It's just 5, 0, comma 5. So notice, going back again to the original one, a sub, if you look at the leading term, a sub n, okay, so that one is 1 and it's positive, and the leading term, the exponent is odd, so it ultimately looks like x cubed, which means we are talking about the following n behavior, the first and the third quadrant. That's the meaning of it. So therefore, we write when x goes to negative infinity, f of x goes to negative infinity, that means the third quadrant. When x goes to positive infinity, y or f of x goes to positive infinity, that also means the first quadrant. Okay. Putting them all together, looking like this, and this is a better looking graph. We want to graph this, and it is in the format that we want, meaning factored form. So it's easy to see the x-intercepts at 2, 0, and negative 3 half 0. This has multiplicity 1, this has multiplicity 2. So 2, 0, multiplicity 2, and negative 3 half 0, multiplicity 1. So we put those two pairs. And I like to put a little arrow here, which represents what we do in calculus, which represents a point that it can cross. Later on, we see that it represents a local max or min. Now, y-intercept. If you replace this with 0, you get minus 2. Squared is 4, times 3 is 12. So you get 0, 12. So plug in 0. Negative 2 squared is positive 4. This goes away, times 3 is 12. And so you have that pair. Now, what matters is the end behavior. To understand the end behavior, if you square that, you get x squared times 2. You get 2x cubed and the rest of it. Just pay attention to this one. This looks like x cubed because n is odd and 2 is positive, which means, again, the first and the third quadrant. That's as far as the end behavior is concerned, everybody. So what does that mean? As x goes to negative infinity, f of x goes to negative infinity. As x goes to infinity, f of x goes to infinity. Looking like this, and this is a better graph. What is the least possible degree of the polynomial? Write an equation for the polynomial graph. Well, the least is 4 because you have 1, 2, 3 terms. And remember, the number of terms is n minus 1. So we want to write the function. We are going to look at 3 zeros and multiplicity 1, multiplicity 1. This one has multiplicity 2. Okay, class? Because it bounces back. So the function would have here x minus 3, here x, my apologies, plus 3 because this is negative 3. Let me write that. And this is negative 3. So it's x plus 3. This is negative 2. So it's x plus 2. And this is 1. So x minus 1. And this one to the power of 2 because of the multiplicity 2. And we don't know what is our initial, value. In other words, we don't know the leading coefficient. We say something such as a. So we are going to write a, something we don't have, we will find out. This gives us x plus 3. This gives us x plus 2. This gives us x minus 1. Multiplicity 2 gives us the exponent 2. All we have to do, pick up a pair, an easy pair, for example, 0, 3 is the y-intercept. And from there, we can evaluate the value of a. That's all we have to do. So plug in 0, you get 3. 0, you get 2. 0, you get negative 1 and squared. And so this is positive one because you square it times 2 times 3, 6. Just drop the 3. And so you have 1 equals to A equals 1/2. Plug it in, you're done. So that's pretty straightforward, everybody. Find the degree leading coefficient and maximum number of real zeros of the polynomial f of x equals 2 plus 3x to the power of 6 plus 4x to the power of 7 minus 6x. Also describe the end behavior or long run behavior. So the first step is to put this in descending order. So we're going to say f of x is 4x to the power of 7 plus 3x to the power of 6 minus 6x plus 2. Here's your leading term, which means the degree is 7. The leading coefficient 4 is positive. Degree 7, or you can say odd. Leading coefficient is 4. Because the degree is 7, the maximum number of zeros must be 7. Because 4x to the power of 7 has a degree which is odd and a sub n is positive, then it behaves like x cubed. So 4x to the power of 7 is the leading term. N is 7 or odd. A sub n is 4, so behaves like x cubed. Meaning what? As x goes to negative infinity, so does y. F of x goes to negative infinity. Again, I emphasize f of x is the same as y. As x goes to positive infinity, f of x goes to positive infinity. Or y. Use number of zeros theorem and Descartes' rule of sign to discuss real zeros of f of x. Fill up the table. So it's important to understand what's going on here. This has to be in descending order. It is. So far, so good. Then you look at the leading term, 3x to the power of 7, and n is 7. So the maximum number of zeros would be 7. The total would be 7. Now, let's read this. Descartes' rule of sign, determine the number of positive and negative zeros. Let f of x be the polynomial f of x equals a sub n x to the power of n all the way to a sub 0. With terms in descending powers of x, a, the number of positive real zeros either equals the number of variation in signs occurring in the coefficients of p of x or is less than the number of variation by a positive even integer. So in other words, just look at this one. And I hope you recognize that what happens here. Positive, negative, positive, positive, negative, negative. So first, let's just write the signs. Again, positive, negative, positive, positive, negative. So from here to here, there is a change. From here to here, there is a change. There is no change here. Here to here, there is a change. And there's no change here. So we have 1, 2, 3 changes here. Now, part B. The number of negative real zeros either equals the number of variation in signs occurring in the coefficients of p of minus x or is less than the number of variation by positive even integers. So we are going to evaluate f of minus x. And remember what happens. Anything that has the odd exponent change, changes and even does it. So if I put minus x here, becomes 3 times minus x to the power of 7. So this becomes minus 3x to the power of 7. This doesn't change because I'm going to change the x to minus x. The exponent is even, doesn't change. This one x is, the exponent is odd, becomes minus 3x cubed. The exponent is even, remains plus 2x squared. This one changes to plus x and minus 3 remains. Now, let's look at the signs, negative, 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 positive, positive, negative. Let's just look at the signs. So no change, no change, there is a change here. No change, there is a change here. So we see that there are 1 and 2 changes. So 3 is the number of changes for the positive, and 2 for here. They have to add to 7 should be 2. 3, 2, 2. The number of imaginaries, and they happen in pairs. Now they go down by 2, so this can go down by 2, becomes 1. This can remain or go down by 2. If it goes down by 2, this becomes 1, this becomes 0, and therefore this must become 6 because they must add up to 7. Sometimes one of them may not go down, so this goes down, but this doesn't. If this is 2, 2 and 1, 3, subtract from 7, that means 4 imaginaries in that case.